Okay, hello everyone. So we come to the last session of today's workshop, which is entirely focused on the deployment of zero emission buses. As we know, there's a lot of momentum across the country and elsewhere in the world, a lot of excitement about zero emission buses, which are very promising technologies, but they come and present a whole host of challenges and issues which require studies and investigations and research. So we're going to have three presentations today that the first one is going to just set the foundation, and the next two are going to present some solutions that we're trying to contribute in this area. So the first presenter, who has already presented twice before, Diego. So again, for those who haven't been with us in the morning, Diego has a PhD in computer science, and he has been a postdoc fellow at the Transit Analytics Lab for the past 2 years. His research really bridges the gap between public transit and cutting-edge computational methods. So he tries to apply AI and machine learning methods to different transit problems. Outside of academics, he's a black belt. He has a black belt in Brazilian Jiu-Jitsu, and he also teaches the sport at U of T. Okay, over to you, Diego.
Thank you, Professor. Can you hear me? Can you see my screen?
Yeah, we can see your screen and see you as well.
Okay, thank you. Let me. Okay. Okay, thank you, Professor. In this presentation, I will cover some insights from the literature, events, webinars, and conference on zero emission buses, or ZEBs. So let's start with the big picture of ZEBs. In 2015, with the Paris Agreement, signatory countries of the Global Pact committed to achieve zero carbon emissions as one of the main goals of the agreement. Zero emission buses can be pure electric or hydrogen, or a mix between hydrogen fuel and electric batteries. So the targets are aggressive for Canadian transit agencies that need to achieve 40 to 45% reduction in 2005 recorded emissions by 2030 and 100% by 2050. So for those who think that is enough to just buy an electric bus and the problem is solved, sorry, but you were wrong. So the purchase of vehicles represents the smallest of headaches. So questions such as what type of charging strategy, if it's low or fast charging, or where to put opportunity chargers, which routes to prioritize in electrification. So these are some of the questions that transit agencies have gone through or will have to go through when making the fleet replacement. Okay, when we zoom out the entire chain connected to the transit agencies, we realize that the problem is not restricted to their decisions. So it's a whole chain that needs to be renewed, rethought, and reformulated. So new actors will enter this long chain, and the change is more structural. Sorry for the... So in each box, we observe the issues that affect each actor in this picture, which are quite a lot and are relevant to the design of this new transport service scenario. In this big picture, we are interested in transit agencies and operators. But before talking about these actors themselves, I would first like to share how academic research on the topic is going. On this slide, it is the result of a 2020 survey paper in which approximately 1,500 papers about electric buses were analyzed by the authors, spanning the years 2008 to 2020. So the first observation is that the research has grown fast and is mainly led by China, as it was one of the first countries to deploy electric buses on a large scale. Canada appears in the ninth ranking position, but much of its effort in public transit is recent, and most transit agencies are still running feasibility studies. In the same paper, the authors indexed the papers by their keywords and plotted this figure showing where the research is mainly concentrated. Out of the 5 clusters they classified, energy management and sustainability concentrate the greatest diversity of topics overlapping the word electric buses. In the fleet operation class in blue on the left, the highlight is charging infrastructure, costs, economic analysis, and batteries. So scheduling appears timidly on the left side, but this is where operational research is mostly focused today. Recently, our lab also surveyed papers from the last 20 years and identified that 80% of the papers focused on charging networks, electric vehicle scheduling, single and multiple depot strategies, and charging strategies. So very few papers addressed operational problems. So this figure shows similar finding. And we are still scratching the surface on the tactical and operational side, and many research opportunities remain to be explored. Okay, one example, a problem that has arisen from the replacement of the fleet by electric buses is bus range limitation. Due to various battery storage capacities and specification, the buses travel a distance that is generally less when compared to the combustion vehicle. So these differences have been reduced over time as battery research and technology have advanced, but it still represents an important problem to be solved since it is linked to the fleet management and operation process. In order to understand the consequences, a lower range will increase the number of blocks in the vehicle schedule allocation, increasing the number of buses that need to serve the operational, since the replacement is not one-to-one ratio. Consequently, increasing operational costs such as drivers, maintenance, replacement parts, and garage retrofit. Quite a lot. Okay, another problem related to the operation is the transition phase, where diesel and electric buses will coexist, or ZEB buses, making the problem of optimizing the mixed fleet an even more difficult problem given the number of variables and parameters that must be included. So the transition problem mainly affects large agencies, and less accurate decisions in this phase will imply additional costs due to inefficient fleet use. So the path to zero emissions is not a straight line, as you can see, and we require careful planning at all levels. Okay, and speaking of planning, the traditional framework that previously followed a linear flow with decisions that started at the strategic layer should be reviewed as well. So we can assume that the strategic level more or less is already at a more advanced stage, as many agencies, at least the medium and small size, have already decided on battery charging infrastructure and what is the strategic decision on infrastructure. However, even for those who already have selected the operational model, they will have to adapt to the new decision-making flow. So this is how we see the planning framework update. So in this new context, the interdependence among decision layers will increase with emphasis on the tactical and operational levels, which in addition to reviewing the flow of decisions, we'll have to check the methods and processes whereby some traditional problems are currently solved. So according to the Opta report published last year, the technology must be suitable for the network rather than the opposite. So in this strategic layer, decisions on which technology to use should be linked to emerging transit modalities and urban mobility philosophies. As previously mentioned, the transition phase, where the vehicle fleet will be hybrid, is one of the main points of attention in planning ZEBs. So the operational department should be equipped with tools for daily decisions about the mixed fleet. In the tactical layer, the impact will be mainly on timetabling processes, vehicle scheduling, drivers scheduling, maintenance staff scheduling. So all the scheduling stuff. So in this layer, decisions are largely supported by IT tools. So however, software development companies are still researching and collaborating with the academy to update their products. So current solutions still need to be prepared to deal with each transit agency's decision. So new variables and new parameters, since the operating model is not standardized and will strongly depend on local features and local conditions. The operational layer, where day-to-day decisions are taken, will be greatly affected by problems during the transition as well. So as highlighted on this slide, verifying work assignments for each ZEB multiple times daily will become arduous, time-consuming, and difficult to manage manually. Thus, decisions should be data-driven and rely heavily on automated tools. So indeed, the transition to ZEBs will require a strong IT strategy for developing new tools and be ready to deal with the massive use of data. At all levels, especially in the tactical and operational layers, data-driven decisions will be crucial in optimizing the service. Here, we are not limiting the options to more sophisticated mathematical modeling, but also visualization tools, dashboards, performance indicators, and decision automation through learning methods. Despite not being the focus of this presentation, transit agencies are living a crucial moment to review their technology architectures and adjust their system to an increasingly integrated and data-oriented business model. We want to emphasize problems at the operational level to share our recommendation with transit agencies. Even the feasibility tests are relevant data so that we can anticipate the modeling of some operational problems. So if we can access this data, is quite helpful to update all this range of problems that we are showing on the slide. So we list the main applied problems, so some of which are known from day-to-day operations and will be impacted to a certain degree by strategic and tactical decisions. So in this section, we will have a presentation of energy consumption analysis that can give us ways of thinking, solving problems using computational methods on energy consumption. Yeah. Okay, so the future or rather the present of the challenge in implementing ZEBs lies in identifying the most relevant tactical and operational problems, using data in its most diverse representation, and adopting new optimization methods combined with learning methods. And collaboration is at the heart of all this, because just like the challenges in climate change, those problems can be solved in partnership. So I'm sure our team is eager to collaborate more closely with companies and transit agencies. Thank you very much.
Thank you, Diego. So yeah, as Diego showed, there's the advent of electric buses is going to require an overhaul, really, of the entire planning process at the strategic level, tactical level, operational level. So the range limitation and the extended length of time required for charging buses is going to impact severely all scheduling tasks and also any operational management and control methods, conventional ones. They need to really adapt to the new reality of electric buses and the limitations that they present. So we're going to talk about in the next two presentations about two efforts, recent ones. The first one is by Lorna Licollari. So Lorna is recently completed her Bachelor of Applied Science in Engineering Science, majoring in Electrical and Computer Engineering at U of T. So for her undergrad thesis, Lorna worked with us at the Transit Analytics Lab on optimizing the planning of charging infrastructure for battery electric buses. And on a personal note, in her spare time, she enjoys biking through and exploring different areas of Toronto. Lorna, please take it away.
Sorry, I noticed that I was muted.
Okay.
Hello. So, yes. So as we mentioned, this is one of the two efforts to kind of tackle the additional planning constraints that come with zero emission buses. As Diego mentioned in his much more comprehensive presentation, there are many additional considerations with battery electric buses. This project will focus on primarily the placement of charging infrastructure, as well as integrating that with the charging scheduling of battery electric buses. Sorry. So just a little bit of background within the context of battery electric buses. There tends to be 4 primary modes of charging. There's in-depot charging, which is essentially what it sounds like, where chargers are installed in the depots or in garages, typically charged overnight, and these chargers tend to be slow chargers, around 150 kilowatts. And then we also have wireless and en-route charging, which to a certain extent are both chargers that operate along a bus's travel. So wireless chargers are typically installed along a road, and en-route chargers are non-wireless chargers that are installed at stops or at terminals. Both of these tend to be faster chargers, with wireless chargers typically ranging from 100 to 300 kilowatts per hour, and en-route chargers can be up to 600 kilowatts an hour. Another kind of novel approach is battery swapping, where battery electric buses with removable batteries are used. These batteries are fully charged and then swapped during daily operation. So within the problem of optimizing battery electric bus charging infrastructure, there are a number of approaches, each taking on a slightly different perspective with some combination of characteristics that relate to the context of the problem, which generally you'll see either an electric or a mixed bus fleet composition of buses, where the problem is focusing on a full replacement of a bus fleet versus an existing mixed fleet and kind of the transition period. There's also the different charger types and charging modes that we discussed previously. So the charging speed, the mode, the capacity of the chargers, and the cost. There's also the decision scope, which kind of reflects what the problem is trying to select, which parameters involved in the system are assumed or given, and which parameters are being optimized. We also have the operational characteristics, which tends to be the charger location. Are we putting chargers in the depots only? Are we putting chargers along terminals? Or are we also considering the possibility of intermediate stops with chargers installed? We also have the schedule constraints. Are we starting from scratch and scheduling our buses based on passenger demand, or are we just limiting the wait time at different stops? Are we relying on meeting existing planning bus headways or existing timetables? And the last category in this respect is energy-related characteristics, which essentially represents the breadth of energy considerations that go into the optimization problem. Are we looking into a more detailed representation of the power grid and grid capacity, or infrastructure decisions like transformer locations? And do we have a robust energy consumption model for our buses, which accounts for all of the different factors involved, which could include temperature, battery characteristics, traffic conditions, weather conditions. And I think that's the next presentation we have will kind of focus more on this side of the optimization. And within the context of this problem, there are a few areas that we are focused on developing, particularly in the context realm, the decision scope. So we are interested in the scheduling of vehicles when with explicit consideration for the charging schedules, where we kind of try to tackle both problems at the same time. We're also interested in placing chargers not only at depots and terminals, but also at intermediate stops. And in terms of schedule constraints, when you rely on, say, a timetable or bus headways, many solutions tend to make assumptions about the underlying block schedules and vehicle schedules, which are important when planning out the charging of these vehicles. So in terms of the research objectives, it's kind of two primary areas. We have the design of a generic solution for optimizing the en-route charging infrastructure. And we have a numerical analysis with a simplified model structure and applying that to data from a Canadian transit system. The generic model is designed to kind of support potential more robust representations of a number of characteristics, including charger characteristics, energy consumption models, and more complex electricity cost and infrastructure systems. In terms of framing the problem, as I mentioned previously, the focus is to maintain an existing block schedule with a fleet of battery electric buses by placing the chargers and scheduling the vehicle charging. This fleet will be entirely electric. All bus stops, including terminals, are options as potential charger locations, and we assume that there will be chargers at depots so that at the start of daily operation, all vehicles can be fully charged. The transit network in our problem will consist of multiple bus routes that are being served by the bus fleet. And the constraint for vehicle charging is that we must maintain vehicle block schedules, so we're not adding any additional wait time. You might notice that in this framing, we are considering a single block schedule, when the reality is our charging infrastructure will support a system through multiple different sign up periods with a block schedule associated. So one of the next steps that we'll discuss later in the presentation would be to kind of consolidate the different solutions for different candidate block schedules. And this could be solved as a set covering problem. So in terms of the problem structure, we have a network of potential charger locations, which in essence is stops and terminals. Each route in our system spans a set of possible charger locations. We set up our block schedules as a set of blocks where each block represents a vehicle's activity over the study period, which is one transit operation day. And each block consists of a set of trips where in each trip, the vehicle operates along a route. So in terms of the model overview, both the generic and simplified model are constructed as MIP problems according to the structure shown on the slide here. So in terms of decisions, we have the charger locations. We also have the charging events, which is essentially an instance of charging your vehicle at a particular time. Our objective, of course, is to minimize overall costs, which is comprised of capital costs to install chargers at given stops, and operating costs, which is essentially the cost of charging our vehicles. In terms of constraints, we have three different categories of constraint sets. We have constraints surrounding the state of charge of a vehicle, which constrains the charging and discharging of a particular vehicle. We have constraints to maintain the physical capacity of a charger, i.e. we have one charger at a bus stop, we can't have two buses charging at the same time. And we also want to constrain when a vehicle can and cannot charge, which is essentially the vehicle can only be charging when it's idling at a stop that has a charger. In terms of the numerical analysis that we did during this project, we relied on data from the MyWay system. So I just have a quick overview of the MyWay transit system here. You can see the annual ridership of 36.6 million. There's a fleet of 623 buses, which currently are a mixed fleet of diesel and hybrid. We have 56 local and 9 express routes. You have over 3,000 stops, and there are 2 depots. I also, in the image here, have 4 routes highlighted. The reason for this is because these are the routes we focused on in our base numerical solution. Here you can see on the side, we have a depiction of the final solution with the chargers placed. You can see the 4 routes in the different colors with labels, and we have 7 chargers placed along these 4 routes. You can see that we have some overlap. So even though each route ranges from 4 to 2 chargers, because of the overlaps, we only have 7 chargers in total. The model was solved using Garobi. And as I mentioned before, MyWay data was used, specifically GTFS data from the static feed. And then the second half of the integrated problem involves the charging schedules. Obviously, the charging schedules operates on a per block basis, so it would be difficult to show it all on one table here. But on the side, you can see the image. We have a partial sample schedule for a bus which operates on the 3 Bloor route. You can see that it starts its journey at the city center terminal. It completes one trip to the Kipling terminal and then charges for 3 minutes, after which it goes all the way back to city center terminal and back to Kipling again to charge for 3 minutes. And then on its next set of trips, it decides to charge at this intermediate stop here for 1 minute before proceeding on its journey. And then another useful set of data to look at here is the total time charged at each of the chargers. You can see the 7 chargers listed here, and it's pretty clear that the terminals are where the buses tend to charge for the longest, which makes sense because that is also where they're idling for the longest. And you can see that for some chargers, like this Winston Churchill Boulevard charger, we don't need it very much, but it's important for the, we need it as kind of a pickup during the operation. So in terms of general analysis ideas we can take from this, it's pretty clear that charge replacement is favored for certain types of stops. Of course, stops and terminals where vehicles idle for a longer period of time are much more likely to have chargers there, which makes sense because putting a charger at these stops can give us higher charging gains when we are planning the charging schedules. It's also clear that because we have a greater number of buses passing through stops where multiple routes intersect, it's also more cost effective to install chargers at those locations as well. It can be observed that often chargers are placed at route terminals, but this is not always a straightforward rule, especially with more complicated transit networks with more route intersections. There still is some benefit that could be gained from considering intermediate stops as potential charger locations. And then another important element of analysis is looking at the sensitivity of the model, because obviously this is a simplified model that we're looking at for this project. So there are potential areas where real world data could significantly impact the results. And we can see that when we vary the state of charge lower bound, which is essentially the lowest that our state of charge for a bus is allowed to reach. It cannot go below that value. As we increase this number, the number of chargers that we have to install, of course, increases. This is kind of a reflection of different battery electric bus charging strategies. For example, one charging strategy could be don't charge the bus until the battery is almost depleted or quite low, and then you charge for a longer period of time. Or the alternative is you have more frequent charging, even when your bus isn't necessarily at a very low point. You just keep the level of charge higher. The other important parameter to look at is the vehicle discharge rate. For this research, we used an estimate that was very simplified and a linear discharge rate. But obviously the energy consumption of the bus relies on a number of factors. And so it's also useful to see that as the discharge rate increases, of course, the number of chargers installed is also increased. In terms of contributions, as I mentioned before, this work created a generic model which considers both terminals and intermediate stops, and explicitly decides the vehicle charging schedules for each of the blocks. And the focus is on supporting existing block schedules instead of trying to add buses or add wait time to schedules, and just see what kind of charging infrastructure we can build based on that. Of course, there are many possible directions to extend this, and many next steps. A few are listed here. One of the first extensions that should probably be made is to develop a system, again, potentially using set covering, to consolidate the different charging infrastructure solutions for multiple candidate block schedules. It's definitely not true in a practical circumstance that we can only have one block schedule. And so it's important to make sure that the charging infrastructure can cover many different candidate block structures. And alongside this, it's important to investigate the impact of overfitting to a particular block schedule. It would also be useful to conduct a numerical analysis with more robust energy consumption models, charging models, and cost models, and also a full system analysis of the MyWay network, just to see what kind of charging infrastructure could be required based on the existing schedules and fleet. Thank you very much. This concludes the presentation.
Thank you so much, Lorna. Indeed, a lot of work really went into this. It's a very complicated problem, so it was a very interesting study to actually try to combine both the optimal decisions on the charging infrastructure with the charging scheduling as well. So congratulations for doing so. So our last presentation of the day is by Kareem Othman. Kareem, again, we introduced him before, but for those who are joining us now, Kareem is a PhD candidate in the Department of Civil and Mineral Engineering at U of T. His PhD thesis is focused really on exploring and developing advanced real-time transit management strategies in urban arterials, leveraging connected vehicle technologies. We told one fun fact about Kareem. A second one is that he has a passion for collecting souvenirs from every city he visits. So his shelves are pretty much like a mini travel museum. Kareem, take it away from here.
Thank you, Professor Amer. Can you see my screen?
Yes, we can.
So for this presentation, I will focus on the prediction of electric bus battery consumption rate using some machine learning methods. And before I start my presentation, I want to highlight that this is still a work in progress. So what I'm going to show here is initial results. Okay, let's start with a motivation. Like usually the manufacturers provide you with the maximum bus range, and this range is actually taken under some certain conditions. But in real life, actually the bus is operating in a stochastic environment, and like the bus operations is really affected by a wide range of factors, including traffic conditions, the number of intersections, the bus stops, and the passenger loading, and even the temperature is one of the main factors that really affects the bus energy consumption. So what we really need here is that we need a prediction model that really help us in the appropriate planning, and that help us to really know when this bus will need to be recharged. So what what we are trying to build here is some sort of a model that really facilitates the planning or scheduling of our electric buses. So in the literature, we have two types of models. The first one is based on simulation studies, and usually simulation studies are used just to understand the relation between some inputs and the energy consumption, and they are not really prepared for prediction. And the second type of studies is real-world studies that's based on real-world data, and usually this is the one that's really used for predicting the energy consumption. And our study is really one of the real-world studies. So what are the gaps? When we really look at previous models, they are mostly dependent on some latent variables. What I mean by latent variables is that they built the prediction models based on, for example, the driver behavior or based on the actual stopping events. But if you are planning or doing a planning for electric buses or building your schedules, you have no idea about the driver behavior. So this information are not really provided in the planning stage or in the scheduling stage. You have no idea about who is driving the bus, what's the behavior of this driver. You have no idea about the actual numbers. So what really happens here is that we are trying to rely on data that are really available at the planning stage. For example, instead of using the actual stopping events, we are using the potential stops. For example, we know that the bus will be stopping as the bus stops, and it might stop at the intersection. So we are including the potential stops, for example, the number of bus stops and the number of intersections in our route. So our objective here is to build a model that facilitates the planning and building our transit scheduling. And actually, when you look at the literature, you will find a large number of prediction models that have been built all over the world, but none of these models were really developed in Canada here. So we will be building our first electric bus consumption model here in Canada, and it's going to be based on the TTC, electric bus. And let's go. Let's explore the TTC fleet and the dataset we have used. So the TTC is really operating 60 electric buses. 10 of these buses are manufactured from BYD, 25 New Flyer, 25 Portera, and actually this makes the TTC is the largest transit agency that actually operates the largest electric bus fleet in North America. And these buses have been operating since 2019 as a part of the TTC Green Bus program that really targets 2037 to full transition to a fully electric bus fleet. And actually, the city is planning to move to zero emissions by 2040. So we are moving rapidly to fully electric buses and fully our zero emission city. So like this actually emphasizes the need for some prediction models and really to have some proper planning and scheduling for electric buses. So what's really the main advantage of what the TTC is happening is that the TTC is testing these three types of buses simultaneously on the same route, which allows you really to compare the performance of every bus under the exact same condition. So in our prediction model, we'll use the average energy consumption rates for the 3 years, 2019, 2020, 2021, to build our prediction model. All right, let's look at the performance of the different bus types. So this figure is showing a box plot for the three bus types. The blue one is showing the energy consumption, the average energy consumption in the y-axis, and the blue box plot here is showing the data for New Flyer, the red one for Portera, and the red one is really for BYD. And as we can see here, we can see that New Flyer is really having a very narrow range. Around 50% of the average energy consumption rates are actually ranged between 1.2 kilowatt hour per kilometer to 1.4. But we can see there is a big variation for the Portera and BYD data. But actually, this figure might be a bit misleading. It's just showing the entire data set and the distribution for the entire data set. What happens by season if you draw the same figure for the summer data, you will see that the three bus types almost have the same range, and BYD have a slightly lower energy consumption rates. And when we draw the same figure for the fall data, you will see that BYD is really the best in terms of performance when compared to New Flyer and Portera, and it has even a smaller range here. But when we look at the winter data set, we will see the opposite is really happening. We'll see BYD is really having a very high energy consumption rate, and it has really the highest bus range, or the highest range for the energy consumption. So really in the summer, you will see that in the summer and fall, BYD is really the one that achieves the lowest energy consumption rates, but in the winter, New Flyer is really the best option. So we can tell that every bus type is performing differently at different seasons. Like for example, in the summer, BYD is better. In the winter, New Flyer is. All right. So for the modeling inputs, we have really 4 types of parameters. We have vehicular parameters such as the bus weight, the front shell area, the motor power, but the battery capacity, and the bus type. And for the operational variables, we have the average bus speed, the average stop spacing, the number of bus stops, the number of signalized intersections, the average passenger loading. And for the route characteristics, we have the route length, the route location, downtown, non-downtown route. And we have external variables such as the average temperature, the average wind speed, and the bus age. And as we can see that none of these parameters are really latent variables. All these parameters should be available and known at the planning stage. All right, so let's talk about the methodology. So in our work here, we will be testing 26 different models, and these models are belonging to different families. For example, the linear family, the decision tree family, and we have 2 stages of analysis. The first stage is to develop one prediction model for the 3 bus types, for the 3 types of buses. And here the workflow is starting really by testing the 26 model. We are not optimizing the model, but we are just testing them. Then identify the family that really achieves the best performance, and then identify the method within this family that achieves the best performance, then optimize the hyperparameter. And in stage 2, as we have different performance by bus type, we are developing 3 different models, one model for every bus type. So in this stage, instead of just starting and testing the 26 models once again at every bus, so we are starting from the identified family we have identified in the first stage, and we will be testing this family to really find the optimum or the methods that really achieve the best performance, and then optimize its hyperparameter. And let's start with the stage 1. And as I mentioned, the stage 1 is focusing on developing just one prediction model for the entire data set. And I wanted to start by the linear model, because the linear model are actually one of the most common methods that have been used in the literature for developing consumption models. But one of the main issues in these models is that they are sensitive to multicollinearity. And actually, in the literature, you'll find that there is a large number of studies that really ignores multicollinearity. And when we look at the correlation matrix here for our data set, we will find that there is a large or there is a high multicollinearity between some of the inputs. So we really need to deal appropriately with multicollinearity in our data set. So instead of just using the traditional linear regression models, we will be using the lasso and ridge regression. And these models really focus on penalizing the model for adding any additional parameters. So we are trying to select the minimum inputs that really achieve the best performance. The lasso regression is very similar if you are using machine learning. It's the L1 regularization term, and the ridge regression is the L2 regularization. Let's get to the results of the linear model. And we have, in this slide, we have the results of the lasso, ridge, and elastic net regression models. And we can see that the 3 models are achieving likely a very low R-square values, R-square of 0.33, R-square of 0.4, or 0.25. So we can really conclude that the relationship between the inputs and the energy consumption is not really linear. So the linear models will not really be working in our data set. And let's get back to the 26 models we have tested. So we have tested 26 models, and finally, the best models that achieves the highest level of performance are the Keta-post, XG-post, random forest, and LGPM, and they are achieving an R-square of 0.61, around 0.55, between 0.55 to 0.61, and just to highlight that these results are not really with optimized hyperparameters. So we still need to optimize the hyperparameters and really test our methods here. And in the next 2 slides, I will show the results of both the random forest and the XG-post. And when we look at the random forest, we are achieving an R square of 0.58, which is better than the linear models. And quickly, when we look at the feature importance, we will see that the average temperature is really the parameter with the highest level of importance, which means that if you excluded the average temperature from your prediction model, you will end up with a model that really performs poorly and doesn't really show a good R square value. And I just wanted to highlight that these hyperparameters are not really optimized yet, so these are still some initial results. And when we look at the XG boost, we will see like a similar performance. We have an R square of 0.6, and again for the feature importance, the highest, the parameter or the input with the highest level of importance is the average temperature. And again, these hyperparameters are not optimal. And in stage 2, we really focus here on providing one prediction model per bus type. And as I mentioned, we will not be testing the 26 models, but we will be starting from the identified four models. So we will start here and test these 4 models, identify the models that achieve the best performance, then optimize the hyperparameter. All right. So when we tested these 4 methods for the 3 types of buses, we will see that every bus type is really the best method to achieve the highest R square value or achieving the best performance, really depending on the bus type. For example, Kata boost is the best for BYD. For New Flyer, for example, XG boost is the best. But I just wanted to highlight one thing when it gets to the R square value and mean square error. You will see that, like for BYD and Cortera, you have a good to moderate R square value with low mean square error. But when you look at New Flyer, you will see that the mean square error is very low, and you have an R square value of 0.24, which is actually, again, it's a very low R square value. And let's dig deeper in the New Flyer data set and really understand why this performance is really happening. When we look at the New Flyer data set and the prediction models for the New Flyer, those are our 4 methods. We will see that the mean square error for these 4 methods is around 0.04 to 0.03, and you have a very low R square value. And the main reason for that is that actually the New Flyer data set had a very small range for the energy consumption. Let me go back quickly to one of the previous slides. If you remember, when we tested or when we showed the performance of the different bus types, New Flyer had a very narrow bus and have a very narrow energy consumption range that around 50% of the average energy consumption are really ranged between 1.2 to 1.4. So you will probably have a very small mean square error, also your R square value is not really good. And even in this data set, if you use the average value or the median value, you are around 0.1 far from the 25 boundary to 25% boundary or the 75% boundary. So you would expect that your mean square error is not really shouldn't really be high, and in the same time you might really not have a high R square value. All right. So lastly, we have compared our model with previous models in the literature, and one of the main issues in previous model is that they cannot really differentiate between different bus types. They just have one model, doesn't really take into consideration the different parameters for the different bus types. So they are producing the same energy consumption for the different bus types. Let's start with one of the models that was developed in Finland. And when we look at the model, it doesn't really take into consideration any of the bus parameters. It really focuses on the TE, which is temperature, the stop density, and the driver aggressiveness. And again, it relies heavily on some latent variables. You have no idea if you are doing some planning. You have no idea about the bus, the driver aggressiveness, or the stop density. And there was a second model that's mainly based on a simulation model by Abdelati and Muhammad. And again, it doesn't really take into consideration the different bus types. So it will produce the same energy consumption across the different bus types. And again, it's heavily based on some latent variables that you have no idea about in the planning stage. And in terms of the numbers, in this table, we are comparing these two models with the linear model we have developed and the Kata boost model that has been developed. And we can see that, for example, in the first model, it was developed in Finland, it was achieving an 0.76 in the original data set that was used in the published paper. But in our data set, it's really achieving a very low R square value. It's even lower than 0.1, and it's achieving a very high mean square error. And the same for the study, for the simulation study by Abdullah and Muhammad. They have reported a very high R-square value, but in our data set, it's not really achieving a very good performance. And when you compare it with our linear models or the kata-post regression, you will see that they are way better than the previous model. All right, let's jump to the conclusions. And the results really, the previous discussion have really shown that the energy consumption is really varying significantly across the different bus types. And this is happening across the different seasons. For example, BYD was the best in the fall and summer, but New Flyer was really the best in the winter. And again, New Flyer really had the most consistent energy consumption rate, that 50% of the energy consumption was between 1.2 to 1.4 kilowatt hour per kilometer. And it's highly, this is why, as the performance is changing significantly from one bus type to the other, it's highly recommended to have separate models for every bus type. And again, we have seen that linear models are not really performing well in predicting the energy consumption rate. And previous models in the literature cannot really generalize. And it's really necessary to build our own simulation or our own prediction model here in the Canadian environment. And that concludes my presentation.
Thank you so much, Kareem. Very interesting work. Okay, so we have some questions. First one to you, Kareem. Have you considered, excuse me, have you considered road grade as a parameter for the energy consumption model?
We didn't really consider the road gradient because, like in Toronto here, the condition, like most of the terrain is really flat. So it's not really going to be a major factor that we need to consider when we talk about the TTC data sets. So we didn't.
Yeah, it's usually a minor consideration here because, yeah, as Kareem mentioned, most of the roads are flat. Another question, very interesting. So BYD operates differently in winter conditions because it has a different battery chemistry. Oh, that's a comment. So yeah, Mark is noting that that's the reason why BYD is operating differently in the winter conditions. Because it has a different battery chemistry. So if you want to comment, or Mark, if you want to elaborate, feel free to jump in as well.
Sorry, I meant to put it in the chat, not as much.
Okay.
It was the wrong box.
Okay, no problem. But if you want to elaborate more, that's fine.
Yeah, just so the BYD has an LFP battery, which is a different battery chemistry than what North American manufacturers have been using. Yeah. And we still don't know if North American manufacturers are going to start switching to LFP, which is mainly used in China.
Mm-hmm. Yeah.
Actually, this is one of the main factors that really pushed us to have a separate model for every bus type, because the battery chemistry and the battery material itself is different from one bus to the other. One of them is using lithium ion, the other is using iron phosphate. Like it's kind of very different. So this is why we were kind of having two stages, one stage for the entire data set, and the second one is focusing one model for every bus type.
There is a question to you as well, Kareem. Does the model account for the interior heating technology used, i.e. the use of auxiliary diesel heaters instead of heating using battery power? So as a continuation, TTC's ZEB testing report notes that New Flyer buses rely on the auxiliary diesel heater more than the Proterra and BYD, which could explain the smaller variations in energy consumption rate in the data. So I don't know if this is something you considered in your analysis or...
No, we didn't really consider it in the analysis.
Mm-hmm.
It's going to be hard to capture what's really happening in the auxiliary diesel, like in the heating condition. Like I'm not sure what every type is using for the heating technology. But yeah, it's a good comment. Like maybe we can really dig deeper to understand why really this is happening and why the range is really smaller for New Flyer.
But there seems to be a lot of questions to you, Kareem. Would you consider dropping off variables with minimal importance and then retrain the models?
Yeah, we are planning to do that. We are gonna use, for example, the parameters that really have the highest level of importance, and we will retrain the model once again. But this is still a work in progress. We have not even yet optimized the hyperparameter. So we will first optimize the hyperparameter, then we will get to this point to consider dropping off the variable with the lowest level of importance.
I know there's a couple more questions to you, Kareem. I'm going to get back to them, but just to also ask both Lorna and Diego other questions. So Lorna, you mentioned that the model was formulated as a MIP. Can you just explain to the audience what this is and elaborate on the model? Because I know you didn't show it here, but which a lot of work went into it. So if you can just elaborate on that.
Sure, yes. So the model was formulated as a mixed integer linear programming model, and essentially the view in the slides was kind of a more simplified for intuition, but we had a few more decision variables involved as just in order to maintain the state of charge of vehicles that had to be decided as the model was it's like during the optimization, and essentially each of the constraints involved could be broken down into a few different mathematical constraints, specifically the charging logistics constraints and the state of charge constraints were pretty important in terms of the math. Yeah.
Very good. Coming back to Kareem, I think there's a question that was touched on the same issue that Peter raised about the heaters. Did any of the buses tested employ diesel heaters? In Ottawa, for example, battery electric buses burn diesel in the winter to heat the passenger spaces, which do not have environmental controls. I guess Peter pointed out that New Flyer relies on auxiliary heating system, whereas both Proterra and BYD use the battery for heating as well. So I guess that answers the question. A question to Lorna. Your analysis of Dundas route indicated charging more frequently than might be needed given the bus range. Is that a policy decision, or if not, why?
Yes, so essentially the Dundas route charging schedule sample that I gave was really relatively a relatively small portion of the total operation of that particular bus. And so within that charging schedule, the charging was done more frequently at the beginning to kind of maintain the charge level to the point where at the end of its operation, the bus was more depleted. So it starts charging less frequently, closer to the end of daily operation. But at the beginning, the goal within that solution seemed to be maintaining the charge at a relatively high rate, just because the constraint of not being able to extend wait times at stops was quite strict. So there wouldn't be very many opportunities to charge for a long period of time. This is something that I guess could be more explicitly controlled in a situation where the actual blocked schedules were planned with bus charging in mind. And that's, I guess, where you would be able to more control this in a more refined way.
Yeah, definitely. There was a consideration also to relax really the block design and integrate this into the problem. But as you can imagine, clearly would make the problem overly complex. And but this is definitely, I think, a potential direction for future research. Good. So